Worked with Red Hat. I've been there for the last 5 years working on the Libvirt project and also on its integration with the QEMU project. So I'm familiar with a lot of interface design and also topic of today's presentation, backing chain management, or how to get your data where you want it. So today I'm going to go over the QCOW2 format, the building blocks in QEMU for managing your backing chains, and then what Libvirt currently exposes and some of the future work that was coming down the pipeline, how to put it together for some neat demos. On the topic of QCOW2, it's been around for a while now. The first documentation was written in 2006, and we all know how documentation lags implementation. I couldn't find when it was actually created. But QEMU copy on write gives the ability to manage what the guest sees without wasting host resources. QCOW2 was added in 2008 because the QCOW original format was severely limited. QCOW2 came along with internal snapshots, reference counting, a bit more structure. It was no longer 32-bit versus 64-bit dependent. Then in 2009, we figured out our headers weren't big enough. We have to track the format of the backing file if we don't want CVEs from probing problems. And we came up with a great hack to inject the backing name into the file. Along the side, there was the QED format that said, we've got a lot of baggage. Can we make performance closer to bare metal? Let's experiment with some new features, and if they pan out, we'll merge them into QCOW2. Well, nobody here uses QED these days because we did merge them into QCOW2 version 3 in April 2012. Among the things we added were feature bits so that now we can negotiate on what the file contains and gracefully degrade with older QEMU opening the file. We added efficient zero cluster management, which makes it even more efficient use of the host resources for sparse file systems and so forth. But all this is just talk and bullet points if you don't know what the format itself is doing. So I'm going to look under the hood. Let's create a new file. 100 megabytes will suffice just for the demonstration. And there is the first representation of what the file does. I looked online and could not find a great image for this, so obviously you can't read it, but we'll try to point out what's important. There's always a header at the first sector. QCOW2 is cluster-based. Everything we do is in clusters. The default size is 64K. You can tune that down to as small as 512 bytes, have your clusters match your sectors. Great until you're working on 4K sector disks. You can tune it up to 2 megabytes. There's some inefficiencies as you get larger clusters for managing copy on write, but there's also some efficiencies, economies of scale as you do larger I/O. So the default is good, but if you need to tune it, you're more than welcome to. Every image contains a ref count table and a ref count block, which is a 2-layer table of here's where every cluster is claimed, or how many times each cluster is claimed from the host's point of view. So with our brand new table, we've claimed 4 clusters, and of those clusters, 3 of them are the header and ref counts that we just described, and the last one is the L1 table, and it's not even a cluster big. So what gives? Well, QCOW2 takes advantage of the operating system guarantees that if you seek past the end of the file, you'll read zeros. So depending on the cluster, if the file is not cluster aligned, read zeros, and you'll be safe. We have an L1 table that describes what the guest sees. So the ref count table is what the host is using. The L1 and L2 tables are what the guest sees. And there's no L2 table because right now the guest sees 100 megabytes of nothingness. So that's boring. Let's add something to it. I'm going to use the QEMU IO command, which is mainly for developers. It simulates data writes to a raw chunk of the file. In reality, you'd probably have a guest file system, but file systems are finicky. The mere act of touching a 1-byte file probably touches 2 or 3 sectors, and if those sectors aren't in the same cluster, that's 2 or 3 clusters. It gets a lot harder to draw. Now that I've got some data, our diagram is a bit more complex. First thing to notice, we added some additional ref count blocks to track that we added new clusters. Other thing to notice is we added an L2 table, and those L2 table 3 clusters of data. So I stuck some memory in the middle of the file near the 99 megabyte mark. I intentionally wrote 65K of data, which was not cluster aligned, just to see what would happen. QEMU is smart enough to allocate the entire cluster and zero pad what I didn't use. And then it tracks in its L2 table, here's the address of every cluster from where the guest sees it to where the host sees it. Then we get to do the fun features that QCOW2 created, which was internal snapshots. Our file has grown even more. We added an L1 table. Wait, we already have an L1 table. Well, the point of a snapshot is that you can have multiple L1 tables in your file. At any given point, an L1 table describes the state the guest would see. Right now, because we just created the snapshot, it's the same state as the file itself sees. The header points to one of the tables. It also points to a snapshot structure that occupies a partial cluster at the moment. The snapshot structure points to the other L1 table. And then through the convenience of QEMU image command, you can pivot between them at will. And part of creating this was we updated ref counts. So for clusters 4, 5, 6, and 7, which is our L2 data, they now have a ref count of 2. We also had to tweak in the L2 table, there's a flag, ref is 1. In the L1 table, there's a flag, ref is 1. The flag got toggled so that future operations don't have to consult the ref count every time. They can just look at the flag and say, am I the lone owner of this cluster, or am I going to have to worry about copy on write? The data specification does point out that the ref is 1 flag is only valid for the active layer. If you're reading an L1 table through the snapshot table, you have to compute things every single time because you don't know if some other code branch has changed references behind your back since the snapshot was taken. But as I said, snapshot with no data is boring, so let's add more data. This time I'm going to write 512 bytes into an existing cluster. And this is where copy on write takes in place. QEMU said, we've got a cluster there, copy the tail end that didn't change in my write so that it's also present in the data, write my new data, and because I have a new cluster, I need to describe it with an L2 table. Oh dear, that means we also have to clone the L2 table. So it changes the ref counts. We have fewer counts that are 2. Some of them went back to 1 because there's now additional clusters. A lot of the data is rearranged, and we have our first case of a file where the order that the clusters appear in the host is different than the order the clusters appear in the guest. Makes for some interesting trying to figure out where your data lives, but it's manageable. Computer does it for you, right? And again, as I said, there's 2 L1 tables. Depending on which L1 table you see determines which other clusters are used together to form whether the guest sees data or sees the empty bytes that were there from before the snapshot. Internal snapshots are fun. What about external snapshots? I'm going to create a new file. This time, call it wrap.qcow2. It's back to our original 4-cluster first-time created file. This time, the part that makes it interesting is that we wrote into the header some details about my backing file as base.qcow2. Used that format header extension to say my backing file is also qcow2. You can mix and match. The base file can be of any format. A very common operation, in fact, in my later slides, is having a raw file as the base and a qcow2 as the wrapper. But an external snapshot without data is no fun, so time to write and see what happens. Here I'm going to fill in some of the data that overwrite some of what was there, and leave in place some of what was there. In this case, write it in between where I had data last time. And just like with internal snapshots, we have to copy the entire cluster to cover the data for the part that wasn't mapped by the write itself. And when we're doing an external snapshot, we always copy from the backing image without paying attention to the backing image's ref counts. Ref counts only matter for internal snapshot purposes. And when we're reading the file, the way QEMU does it is if the file has the data, that's the cluster the guest sees. If the file doesn't have the data, then we go pull the cluster from the backing file at the time of the read, and it's the write that does the copy. So now we have a little bit of a view of what a qcow2 file does. Let's look at how we can arrange it. I mentioned both internal and external snapshots. Let's compare them. With internal snapshots, you have one file contains everything related to the guest. You can even include live VM state, take a snapshot of a running guest, move the file to a different machine, reload that state, and your guest resumes execution as if it had never shut down except for the clock skew. Reverting between snapshots is easy. It was one of the first operations for snapshot revert that QEMU added, and therefore Libvirt added. If you use Virt Manager, that's what you get. There's no I/O penalties to your active state versus your inactive state. Your active image, those clusters are immediately accessible. The only time you have to do anything is if you write to a cluster, you have to copy it, but that's a one-time operation because your copy is now ref count 1. There's some disadvantages. Your backing snapshots cannot be read while QEMU is running, at least not yet. There's ideas of how we could expose that, but right now, if you have a guest running, you cannot get at the data of the snapshot. QMP internal snapshot management is inefficient. We don't have quite as many commands available. Some of the commands require you to take live VM state at the same time as your disk state. Some of them still use HMP. We haven't mapped them to QMP. And it is what it is. qcow2 size, if you use a lot of internal snapshots, your host file can exceed the size that the guest sees by multiplying the factor of however many snapshots you take, provided that, or as your snapshots start to diverge and your ref counts have to be, your clusters have to be cloned, your file can grow quite large. Another disadvantage, there's no defragmentation. qcow2 version 3 added the ability to mark image blocks and clusters sparse. And with newer kernels, you can punch holes back in your file. So on a file system, when you throw away a snapshot, you can reclaim the space. But if you're mapping your qcow file directly on a block device, there's no way to punch a hole in your block device. So it can get a bit expensive if you can't reclaim some of your space and repack the file to be more contiguous. On the other hand, external snapshots, we have a lot of development on it, a lot of new features, and we're continuing to develop new features. Some of the other talks in this presentation have mentioned those as well. Live backup is easy to do. Storage migration is possible. Building blocks, we've focused on trying to isolate things down into the smallest pieces possible rather than doing 5 things in one command, have 5 separate commands, and then the application can combine them how it sees fit. External snapshots are great for thin provisioning. Create a common base image, and then every other VM in your cluster references that base image and puts a QCOW2 wrapper on top for the few clusters that it needs to diverge to be its own guest. On the other hand, with external snapshots, you're now managing multiple files. Deleting snapshots is a bit tricky. Libvirt still hasn't implemented the commands to do it natively, so you have to drop into raw QEMU image calls yourself, and then update Libvirt to have a consistent worldview. It'd be nice if Libvirt could track it all together. One of the other disadvantages is that the more snapshots you take, the longer your I/O chain is. And like I said, for every cluster that QEMU reads, you have to find the first file on the backing chain that contains that cluster. If you have a lot of files, that's a lot of I/O the first time through. QEMU does some caching. The caching helps, but there are benefits to having a shorter backing chain. So therefore, we need operations on our backing chain. A lot of the times on the mailing list, and also in my presentation, you'll see backing chain notation. A, left arrow B, means that image A is the backing image for image B. Image B is the top or the active layer. I'll use some examples based on the diagrams I did earlier in the talk. We also have a nice new command added recently, QEMU image map. Tells you about the file. So with my earlier file, we had 3 sectors allocated, 2 sectors that were written from wrap.qcow2 found at this offset, and a 3rd sector that we read from base.qcow2 at a different offset, all at the offsets that the guest would see them. And if it's not listed in the map, then you can assume the clusters read as 0. A good way to think of backing chains is points in time. If we have A backs B backs C, there are 2 points in time that we capture as a snapshot, and then an active layer. The first point was when we created image B, we captured the state, and that state lives in file A. Then point 2, we captured the state at the point in time where we created file C, but that state lives in the combination of file A and B. And then our active layer is the combination of the state through the entire chain of A, B, and C. With your naming, if you create a file and name it after the timestamp, that gets a little bit confusing because the timestamp of the file is not the data at that point in time. It is the change in the data from that point in time. The timestamp for the snapshot is the data in the backing files. So being careful how you name your files. If you use timestamps, be careful that it's not that the times. If I name a file Tuesday, it doesn't mean that it contains the data as it was on Tuesday. It contains the changes since Tuesday. Read the backing chain to see what Tuesday had. A rule of thumb, do not change your backing files. I know on the mailing lists I get questions, can I update my base image and all my thin provisioned guests will magically see my new content? If you want that, use overlay FS, use multiple devices, update the files in your base file system, and then your overlay files systems will pick up the differences. But that's not what backing chains do. If you modify your backing chain, that is almost a guaranteed recipe for guest corruption. So let's see what happens. I'm going to write into my common image. I have guest 1 and guest 2 both provisioned off of my common image. And I've also shown what the guest sees. And I'm going to write 4 clusters at the beginning of the file on the hopes that my guest will magically start using this new data. Except that guest 1 has clusters locally. Those clusters take priority over the ones I just wrote. So guest 1 sees data that did not exist. Guest 2 had clusters they override what my common base image. Guest 2 now sees data that did not exist. If you get really unlucky, your guest will continue operating and you won't see this corruption for several days or weeks, and then you're really hosed because it's hard to pinpoint why you corrupted yourself. But the rule of thumb is never modify an image externally while QEMU is running it, and never modify a backing image while a guest might be using it. Libvirt does provide some lock management daemons that try to prevent you from shooting yourself in the foot. They're not always perfect, but they're better than no protection at all. Libvirt manages the lock daemon and says, I'm opening this file read-only, therefore nobody else should be able to open it read-write, and protects one guest from corrupting another. Our first block stream primitive, our first block operation primitive is the block stream. We're going to start with chain ABC and copy or move clusters towards the top. Once we've done that, we can rewrite the backing chain to drop any redundant files. With QEMU 2.4, you could copy from anywhere in the backing chain into the active image. So I'll start by taking A and B, take the entire chain and pull it into the top layer. That says I find any cluster that's allocated from the guest view but not allocated in the host, and pull it into the host by copying it from its backing chain. After I've done that, I can throw away files A and B because file C has the same state as it did before, but now we're not relying on our backing chain to provide that state. Or we can do intermediate or a single image, pull file B into file C. Here we only have to copy 2 clusters, and then we have to rewrite our backing chain to point to A. B used to point to A, so now C points to A. And we've gotten rid of B out of the loop. The operation is always safe because you're pulling data forward. The files that you bypass or get rid of out of your chain never change contents, and we've never violated our rules. So the backing files, you can throw them away because you don't need them anymore, or you can keep them around as your backup for your point in time. QEMU 2.5, Berto's working on patches for intermediate streaming, which says shorten our chain but keep our active layer the same. So here we're going to copy the clusters from image A into B if B doesn't have them. So 2 clusters later, and B sees the same contents, but now we can throw away file A. The next fun primitive is block commit. This is the opposite direction of stream. We're going to copy and move clusters away from the top. Again, we can rewrite backing data to drop redundant files. Block commit was one of the first block commands back in QEMU 1.3, but it could only do intermediate files. We could move data from B. Any cluster that was written in B, we could move into file A. Now the contents visible in A have changed. We no longer have the state and time for where A was marked read-only and B was created. We now have the state and time where B was marked read-only and C created. We've thrown away some state and time. We also rewrite the backing file for C to point to A because that's the same contents that it was getting from B, and we can throw B away. Our chain is now shorter. QEMU 2.0 added active commit. Now we can also do the same thing where we commit C into B, and now this point in time that B tracks is the point in time that we did our commit operation. We've thrown away the earlier point in time that it tracked, but if we want, we can throw away a file. We can make B become the active file. The guest never sees a change in data. Or we could keep C alive and just track. And again, C is tracking the delta from the point in time. So the point in time is now when we did the commit, and we could keep C alive and track a new set of delta. Or we can do multi-file commits. Commit C all the way into image A, make A the active image. But here's my caveat. We modified what the backing image sees. The moment we wrote cluster C into backing file A, as long as we're looking at C, the guest data is fine. As long as we're looking at A, the guest data is unchanged. But if we look at file B, we have data that never appeared in the actual state that the guest saw. So it becomes important that as you do multi-file steps, remember what you might be corrupting and be sure to delete those files or take other preventative measures so that you don't try to revert to state that's no longer valid. In fact, there's been talk on the mailing list of ideas of when adding a flag to the commit operation so that when we say we're about to write C into A, but we also check the overlay, oh, there's nothing there, we need to copy the previous data from A into B so that B stays consistent no matter what we've done to A, and then we can cleanly detach B from the chain and merge it all into one operation. The question is, can I do an intermediate stream from A into B and then do my commit from C into A? Yes, but doing it as two steps is less efficient than doing it as a one-step operation that does all. So it's just talk of a possible optimization. Another possible optimization is right now when you write your images to your backing file, the clusters are still written in the base, are now written in two places, the backing file and the active file. So the optimization would be, as we commit files and clusters down into the backing image, can we also clear those clusters from the active image so that the active image can shrink in disk size and we're not duplicating clusters in places. So those optimizations would be optional flags, and they may be coming down the pipeline. There's the efficiency question. If we want to remove the second point in time from A, B, C, D, and remember the second point in time is not necessarily removing file B, but it's remembering that the point in time was where we created file C and have the contents from A plus B. So there are two ways to do that. One is to pull or stream the contents of B into C. Now B is redundant, so we have the new chain A to C prime to D. Or we can commit C into B. And now C becomes redundant, and we have the chain A to B prime to D. Both operations have their merit. It depends on how long you've been running the delta and how much data the guest has been generating. The QEMU image map command can help you figure out how many clusters would I be moving by doing operation in one direction or the other. And again, some of it depends on QEMU stream, does not support intermediate streams until 2.5, so it's still a work in progress to even expose the right interface to the user to quickly determine which is my most efficient. But that is something we hope to be able to provide, is helping a management application choose which of the two directions is more efficient. Another point of efficiency, the question earlier about can you stream first and then commit, that's two operations versus one operation that does it all. Also, anytime you're doing operation, if you do it from A into B, B into C, C into D, you get consistent results, but you may be moving clusters multiple times, whereas if you go from A straight into D, you've minimized the number of clusters that you have to move. So multi-step operations can add efficiency, but they also add the risk of leaving an image in an inconsistent state if you aren't careful where your data is going. Another primitive is the drive mirror. This is where we take one image and, while the guest is running, copy the active layer into a destination of the guest choosing. We can either do a deep copy where the copy created sees everything that the guest saw, or a shallow copy. I'm going to start with a deep copy. In fact, I'm going to start this operation in block stream or drive mirror. Drive mirror is an asynchronous operation where it does the clusters in the background while the guest continues to run, but then the guest can interrupt things and say, I want to write clusters myself. The guest always takes priority. So we're in the middle of a cluster, our copy's not yet complete, but the guest wrote some new clusters, so part of our mirroring operation is the clusters go into both files. And then when we resume the operation, because we have some downtime again, we are only copying files into the copy if they haven't already been written by the guest. But after the operation settles, and it may be seconds, it may be minutes, but once the operation settles, the two files are in sync, and we can break the operation. We can either keep the active layer untouched, break the copy is now a point-in-time backup, or we can pivot and say our active and base chain are no longer in use, they're now the backup, and our copy becomes the new active image. So it's nice that we can take the file and go either direction. That was a deep copy. We can also do shallow copies by pre-creating the destination file to be a QCal wrapper around the same content as the base file, whether it's the same base file or whether it's a copy of the base file. You have some flexibility as long as it's the same content the guest would see. And there, again, the operation is asynchronous in that we copy any clusters from the shallow image. We leave the clusters from the backing image unchanged because we can already see those as they are. If guest data comes in the middle, we clone the guest data between the 2 points. And then when the image is finally synchronized, we can once again choose whether to keep the original or keep the copy as we break the synchronization. Drive backup is similar. It's more recent, added to the tree. That says start a point in time. So drive backup started. The point in time for drive backup is when you break the synchronization. The point in time for drive backup is when you start the operation. Here, we'll start the same partial operation. We start copying clusters from the guest into our copy. And then the guest comes along and says, I want to write data. But instead of copying the data into our active and our copy, we say anywhere that the data touches something that the copy doesn't have, we need to write the old data into the copy and the new data only into the active image. So the active image is always consistent. The old image, by the end of the operation, the old image becomes the point-in-time snapshot. And that point in time is when we started the command. It may take several seconds or minutes for the backup to complete, but as long as QEMU is running, that data is available, and because we're running asynchronously, we will eventually reach the point where your copy is flushed and you have a safe point in time. We also have incremental backup coming down the pipeline for QEMU 2.5, where management can track one or more dirty bitmaps associated with each image. Dirty bitmaps are the workhorse behind drive mirror and drive backup, but we are now making them a first-class citizen. Back to my comments earlier about trying to break these operations into the smallest pieces possible so that management can pull them together in fun and unique ways. Dirty bitmaps will allow you to get the same benefits of QCal2 copy on write even when running with a raw image or something else that does not natively support copy on write. Another benefit of dirty bitmaps is because you control the bitmap directly, you're tracking which clusters are written without having to have a backing chain. So I said earlier that the longer your backing chain is, the more I/O penalty you have as QEMU has to chase the backing chain. Well, with dirty bitmaps, you don't need the backing chain, but you can still track the points in time. Finally, let's look into what some of these operations can do under Libvirt. If you use modern Libvirt and get the guest, dump the guest XML, you'll notice that any backing chain, wrong button. Any backing chain in your guest description will be listed by a nested list of disk, has a backing store, so I have a chain of my base image is the backing of my wrap image, is the backing of my wrap2 image. We can refer to those images by their device name. Libvirt will take the device name VDA and the index 1 to refer to whatever backing store is at index 1. or you can refer to it by file name on the cases where you're using file. If you're using network like Gluster or CEF, it becomes harder to come up with a unique file name, and therefore that's why we came up with the reference by index. Then QEMU, Libvirt takes care of all the magic needed to map the name from your XML into whatever the underlying string is that QEMU needs to see. Creating a snapshot, so making your chain grow larger. Libvirt has supported this through the vir domain snapshot create XML. You can package all your creation instructions into an XML file with snapshot create, or if it's a simple enough operation, we created command line sugar snapshot create as and spell out the individual options, and then the command line is smart enough to convert that under the hood to the XML that Libvirt wants to see. Maps to the QEMU block dev snapshot sync command. Common flags that you'll see in various scripts for using these. The no metadata flag says create the side effect of changing the backing chain and updating the XML to track the new file, but don't track it in Libvirt's. As I said earlier, Libvirt is great at tracking internal snapshots, not so great at tracking external snapshots. We're getting there, but it'll take some more patches and some more love and effort. So in the meantime, if you create a snapshot, Libvirt's tracking this metadata, and then you go change something behind Libvirt's back, then you have to clean up that metadata. So just pass the no metadata flag and track it yourself. Another one is the quies flag. If you have the guest agent installed on your guest, then quies says, please freeze all guest I/O, make the guest disk consistent before I take my snapshot. That way, if I revert to my snapshot, the guest was in a consistent state, I can start running right away. And if you don't use the quies flag, the snapshot you take is akin to what you would have on your disk if you yanked the power plug. Files may be inconsistent, and hopefully you had journaling installed so that you didn't completely mess up your data. Block pull or block stream. Libvirt uses the term pull, QEMU uses the term stream. They're synonyms. And then Libvirt adds yet another name, is the block rebase API. Naming is historical. It's a fact of history. We have to live with it. Right now, since QEMU only supports polling to the active layer, Libvirt only supports it. But as QEMU 2.5 adds intermediate streaming, we plan to reuse the same API and then take advantage of our indexed notation so we could merge from VDA1 from its base of VDA3 to do a backing chain commit along the intermediate images. Block commit, there we at least named the API right. Some example usage, we can take disk VDA and commit the top image of VDA1 down into its base image. Since QEMU has slightly different behavior, whether you're doing a backing chain commit or an active commit, remember with active commit you have to decide whether to keep the original chain or pivot over to the new chain, or pivot to the now committed top image. Libvirt exposes that choice. A lot of the flags, if you pass shallow, pivot, verbose, timeout 60, you get a nice command line progress meter of how far the commit's gotten. If it happens to finish within 60 seconds, you then pivot. If it hasn't finished, then you're no worse for the wear. Your guest is still running. But it's multiple Libvirt APIs under the hood through the single command line, and then those Libvirt APIs in turn are doing multiple QEMU commands. So it's a nice way to roll up multiple operations under a single command line. And again, as QEMU adds features, we plan to mirror those features into Libvirt. Block copy, same story. We have the block copy API, and then once things are synchronized, then you create your point in time by calling block job abort to either abort to the original or abort to pivot to the new copy. Right now, the block copy requires a transient domain, and that's because we don't have persistent bitmaps in QEMU yet. But that's coming down the road. Also, I mentioned earlier we have the drive mirror and drive backup commands both in QEMU. Right now, Libvirt only targets drive mirror, so we have work coming down the pipeline to support both directions. Whether that remains with block copy or whether we create a new API remains to be seen. So in the last 5 minutes, let's see what we can do by putting these together. I want to create a potentially bootable backup of the live state of my disk, or the state of my disk in the guest without any guest downtime. So right now my guest is running with a backing chain, has a base and an image. First thing I'm going to do is use snapshot create to create a wrapper. The name, I created the name temp. That name floated onto the file name, and the only reason I created the name is because otherwise Libvirt uses a timestamp, and as I said earlier, timestamps can get a bit confusing. No metadata because I'm going to undo things after the end. If I want to make it bootable, then I add the QES flag. That requires the guest agent, and not every guest has an agent, so the QES flag is optional. Then I'm going to use a copy. Reflink always is awesome if you have BTRFS. Then the copy is an instant operation. If you have a SAN command or whatever your network storage or storage solution has, if you have an efficient copy, this is the place to use it. As soon as I've created my copy, I now have my backup image, has a base of my base. And then my snapshot or my backup is complete. So all I have to do is clean up after myself, verse block commit, take my domain, take the VDA disk that I expanded, and do a shallow commit, pivoting back in to the original image, and do it verbose so I can watch it happen on the command line. And then remove that temporary file. And again, I created the name so I would know what file name to delete at the end. There's no guest time. With fast storage array, you can do this in less than a second. We need a QCOW2 wrapper, but only for that second that we're doing things. It's pretty amazing that you can take a live backup of your guest. Now that we have this backup, how do we revert to it? So I took a snapshot. I created a file named my experiment, which is going to be the delta since my snapshot, and do something to my guest. And I didn't like that experiment. I want to roll back to my base image. So the first thing, since we're going to be rolling back, we don't need the guest running anymore. Destroy it, which in verse terminology is stop it. Edit the domain. I'm going to take my experiment and edit it back to my base. Remove the now dead experiment and start my domain again. And I've reverted to my external snapshot. And if you have to keep your chain consistent, you may have to throw in some QEMU image commands or copy commands, remembering the rule of thumb that if you ever write into a backing file that somebody else was using, you've corrupted that somebody else. Again, Libvirt doesn't quite manage this. We want to enhance that and make Libvirt make it a little easier to do by without having to resort to doing it by hand. And live storage migration. Let's say our storage chain is running on network storage, and for efficiency, we want it on local storage, but we don't want guest downtime. I don't know why that popped up. Create our snapshot similar to what we've done before. Use our fancy sans copy commands to copy things locally. Now we're going to use QEMU image to create an empty wrapper around our file. Undefine our domain because Libvirt doesn't have persistence bitmaps yet. Do the block copy, shallow block copy. So that says take the data that's in our live wrapper and copy it to our destination wrapper. Since we undefined our domain, we need to redefine it. So dump the XML from the running XML, define it. Block commit, so our wrapper image gets merged back into local image. Local image can be raw. clean up our mess, and if you have a fast copy, you have now migrated your storage with minimal time for the overall sequence and with no guest downtime. And hopefully in the future, as Libvirt starts to support QEMU persistent bitmaps, we can even drop some of those steps about undefine and redefine. There's offline chain management. Right now, Libvirt can only show you the backing chain of a running guest. We need to see what's there for an offline guest. Reverting to snapshots, exposing QEMU 2.5 editions. There's still a lot of fertile ground. Patches are welcome. But I hope that the things I've shown today can give you a feel for what's going on under the hood and how to piece it all together. Any questions?
When you use drive backup, you have the benefit that you can do atomic backup of multiple disks, where you have the same point of time for all the disks in the VM.
Yes, I didn't cover that in my talk, but one of the points of the QEMU commands is there's a transaction command that can group multiple things together. So when you're doing drive backup, you can use a transaction to group multiple drive backups so that all of the drives are at the same point in time.
Yeah, so is there some trick to do atomic backup with drive mirror? I don't remember.
Libvirt can do transactions as well for creating snapshots. I'm not sure if Libvirt does the... Right now, Libvirt only supports the drive mirror, not the drive backup, and the drive backup is where it becomes more important to specify multiple disks in one command. So there is still some Libvirt work to do to expose drive backup, but yes.
But you can use the live snapshots and copy them offline, basically, right?
Right.
Okay.
And again, depending on how you create the snapshot, as long as you pick the point in time and then use the QEMU transaction command so that the point in time is the same for all of your disks, then the copying can be done offline, but the point in time is stable, and so you have a consistent backup across your disks.
This is a kind of high-level question, but so when we want to run, for example, Docker in a VM, for example, right? Mm-hmm. And then typical way is you pull the Docker image, then run VM, and then initially you run VM using some, for example, the QEMU whatever image. Then we need to mount that host file system because Docker file systems are on the host side. Then we use, for example, 9p. That's that kind of table. And then what we want is somehow, we can we want to replace that the host file system with, for example, the QEMU image. But the QEMU image is huge, right?
Yeah, and I think I touched on that. It would be nice to have overlay effects. To get that with a guest, you need multiple drives. You can't do it through QEMU image because QEMU only moves a cluster at a time, and clusters aren't the same granularity as your file system. So to play tricks with Docker and having Docker images that depend on base images, you need tricks like overlay FS built on top of multiple disks plugged into your guest. But I assume that as people figure out and play with overlay FS and figure out how to plug in multiple disks, that you can simulate effects where a guest image becomes the guest disk that is the backing file system for another guest disk. But it's bigger than this talk, because this talk is only what you can do with the single file.
Okay.
Anything else?
So, do the persistent bitmaps also cover the case of a QEMU crash, or just where the user shuts down the VM for some reason? The operations that Libvirt supports on a persistent guest are crash safe. If Libvirt gets restarted or if QEMU crashes or the guest shuts down, the operation itself is not lost. You can either resume it or Libvirt remembers that it was running. The block copy operation that requires a transient guest, that's Libvirt's way of saying, if your guest goes away, my block copy is toast. You'll have to start from scratch. And the hope is that as QEMU adds persistent bitmaps and Libvirt uses persistent bitmaps, then we can make that
also be robust. But the stream and pull operations are robust. I think I've spent my time, so thanks for your attention.